Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So, in today's session, we are going to discuss regarding the financial data analytics using principal component analysis or PCA. What is the learning objectives of today's session? So I want you to be able to define what is PCA and why we use PCA, what kind of approach that PCA do for the model, and we are going to have some demo on the PCA. Alright, so what is principal component analysis? Principal component analysis or PCA is a technique that transforms high dimensions data into lower dimensions while retaining as much information as possible. So basically, the concept is when we have a high dimension data, let's say the data is around 20 dimension. The objective is to lower the dimension into 3 dimension, for instance. Yeah. So this 3 dimension is a standalone data, which representing the 20 dimension of data. In order for us to be able to see the data in a better visualization rather than 20 dimension of data. So in the principal component analysis, we use the PCA to measure the data in terms of its principal components rather than a normal X and Y axis. And it is also important that PCA finds a new set of dimensions, which is standalone. Yeah. And we will rank the dimension according to the variance of data along them. So how does PCA work? In understanding how PCA work, we should have knowledge on the following. We need to have an understanding of the means, variance, covariance, standard deviation, matrix transposition toward the eigenvalues, and the eigenvector. So how does the PCA works? First, we need to calculate the covariance matrix of the data points, and then calculate the eigenvector and eigenvalues. After we have the eigenvector and eigenvalues, we sort the eigenvector according to the eigenvalues in a decreasing order, and then choose the first k of the eigenvectors, and that will be the new k dimension. K meaning maybe we can use 2 dimension or first 3 dimension from the highest eigenvalues. And then we transform the original and dimension data point into k dimension. the original data point using the uh, uh, the scalar into the dimension. Okay, so let's try to do this. First, we need to normalize the data. The first step is to normalize the data that we have so that PCA works properly. This is done by subtracting the respective means from the number in the respective column. Okay. So if we have two dimensions, x and y, all x become means of x and all y become means of y. This will produce dataset whose mean is 0. So let's start and calculate the standard deviation and variance to normalize the data. Second. So this is the example of the data. This is the data. There is feature A, feature B, and feature C. This can be financial ratios, and this is the sample will be the companies. So we need to calculate the means of the data, the average of the A and the standard deviation of the A, also the B and C. After that, we need to standardize the data, normalize using, when we are in Python, we use the standard scalar. Since we are in Excel, we do it like this. So the A, the data A minus the means divided by the standard deviation. So we have the we normalize the data using the z-score. Yeah, this is the z-score data, and then we do it for all data, and in the end the mean becoming 0. Okay, the average of this, yeah, because this is minus and this is, it becomes 0, this is 0, this is 0, and the standard deviation will be 1 and 1. Okay, so we have the z-score of the standard scalar data. Next is, after we normalize the data, we calculate the covariance matrix. The covariance matrix. The covariance matrix formula will be sigma of variable, the first variable minus the means of the variable times the target variable minus the means target variable divided by n minus 1. Yeah. So if it is a variance, okay, the variance of the matrix covariance, we put variance of x1. This is actually representing covariance of the x1 toward x1, and then covariance x1 towards x2, and then covariance x2 towards x1, and the variance of x2 or covariance of x2 toward x2. Okay, so this is using the 2 times 2 covariance matrix. So the variance and covariance are a measure of the spread of a set of points around the center of the mesh or the means. Variance measure the deviation from the mean for points in one dimension only. Example using height. Covariance as a measure of how much each of the dimensions vary from the mean with the respect to each other. Covariance is measured between two dimensions to see if there is a relationship between the two dimensions, example, number of hours studied and the mark obtained. So the more number of hours studied, the more mark obtained. So they will have positive covariance. The covariance between one dimension and itself is called variance. So this is already explained before. The covariance of x toward y is the total of the x minus the x means towards the target variable minus the target variable means divided by total population minus 1. So if you have three-dimensional dataset x, y, and z, you could measure the covariance between the x and y dimension, the y and z dimension, and the x towards the z dimension. Measuring the covariance between x and x, or y and y, or z and z would give you the variance of the x, y, and z dimension respectively. This is representing covariance between dimensions for 3 dimensions matrix. So the diagonal one is the variance. Diagonal is the variance of x, y, and z because it is towards x toward x, y toward y, z toward z. The covariance x and y equal to covariance y and x. Hence, matrix is symmetrical about the diagonal. So covariance x and y equal to covariance y and x. Okay. N-dimensional data will result in n times n covariance matrix. This is the covariance example. So we have here the positive covariance and this one is negative covariance. A positive value of covariance indicate both dimension increase or decrease together. Yeah. Example, number of hours studied increase, the mark increase. A negative value indicates one increase, the other decrease. Let's say active social life and performance in the department. So that is the opposite. If covariance is 0, the two dimensions are independent to each other. Let's say the height of the students versus the mark obtained in the subject. So why bother with calculating covariance when we could just plot the two values to see their relationship? Covariance calculation are used to find the relationships between dimensions in high-dimensional datasets, usually greater than 3, where visualization is difficult. So if we have 3 dimensions, still 3D visualization still okay to be analyzed. But if it is 6 or 7 dimension, it will be highly difficult. That's why. So let's do the covariance. So after we have the standard scalar, normalize the data, and then we calculate covariance. How to do the covariance? Okay. So the data sample 1 minus the means times, oh, this is for the A and the A. For A and B, yeah, for A and B, okay, So for the sample, the company one minus the means of the z-score times the ratio B's. This is financial ratio A, and then times the financial ratio B minus the means, plus financial ratio A of the company 2 minus the means times financial ratio B in sample 2 minus the means, and so on, and then divided by 3. So we have the A and B covariance. We continue to A and C and A and A, B and B, B and C, C and C. Therefore, in the final model, we're gonna have, this is the, we input A to A 0.67, B 0.28, C and A and C 0.28. So we have the covariance. Right. Now we have the covariance ready. And then what next? The next one is to calculate the PCA. In calculating the PCA, we need to find the eigenvalues and eigenvector. By finding the eigenvalues and eigenvector of the covariance matrix, we find that the eigenvectors with the largest eigenvalues correspond to the dimension that have the strongest correlation in the dataset. This is what the principal component analysis is. The PCA is a useful statistical technique that has found application in fields such as face recognition, image compression, pattern, or in data of high dimension. So how do you find eigenvectors from eigenvalues? In order to determine the eigenvector of the matrix, you must first determine the eigenvalues. You need to substitute the eigenvalues lambda into the equation of the A towards the eigenvector equal to lambda times the eigenvector. A is the covariance data. Yeah. So how do you do that? Okay, let's do it. So in calculating how to calculate the eigenvalue and eigenvector. So we have the data of covariance. And then to calculate the eigenvalues, yeah, we can calculate the eigenvalue manually like this. So the feature, this is for the variance, we put another model where the covariance is minus the lambda, the eigenvalue. Covariance plus minus the eigenvalue, covariance minus the eigenvalue. So the question is, what is the value of eigenvalue here, here, and here? So we need to identify the three the number of the eigenvalue for the 3 times 3 matrix. So this is the process on how to do that. So okay, I will not go detail on this, okay, because this is deep into algorithm and mathematical science. Okay, so we have the matrix like this, and then there is differential into model like this, okay, and then going to like this until the final model like this, minus lambda 3, lambda with the power of 3 plus 2.01 times lambda with the power of 2 minus 0.741 times lambda. And then when we do this lambda should be, when we input the lambda, should be equal to 0 here. So in the model, we identify that the lambda 1 will be 1.52. Since we calculate that if we put 1.52 by the power of 3 times blah blah blah, the result will be 0. And then 0.44 for the lambda 2, where the result will be 0 as well. And 0, where the result will also 0. So we identify the eigenvalue of the covariance matrix. After we identify the eigenvalue, next we need to identify the eigenvector. So the concept is like this. The covariance data times the eigenvector equal to eigenvalue times the eigenvector. So in here, for the first lambda, this is the eigenvector that we identify. For the second lambda, this is the eigenvector. And for the third lambda, this is the eigenvector. After that, we summarize for the 3 eigenvalues. What is the eigenvector? This is the eigenvector. How do you get this number? Yeah. By using the manual in Excel, you can do that by calculating the eigenvector. So we have A. Let's say we have A as the covariance. Yeah. So when the this is the covariance, and then we can put 1 minus lambda, 1 minus lambda, and 1 minus lambda for the variance, where the lambda we identify the lambda for the eigenvalue is, this is the example, is minus 1, 1, and 3. So when we put the lambda is minus 1, we can get the eigenvector as minus 1, 1, and 0. And when we put the eigenvalue for the lambda as the 1, and then we get the eigenvector here. And then when we, in the eigenvalue number 3, as the number is 3, 1 minus 3, 1 minus 3, 1 minus 3, and we follow the eigenvector, we get the eigenvector as 1, 1, 0. And this is the final matrix of the eigenvector. This is how to develop the eigenvector that we put into the equation here. So the eigenvector is there. So we have the eigenvector in place. So what next? Next, after we understand the eigenvector, we compress. We continue to multiply the standardized data with the eigenvector. So this is the standardized data. Yeah, the standardized data here using the z-score times the sorted eigenvector matrix, yeah, from the highest eigenvalues toward the lower eigenvalues, and then we get the principal component analysis data, PCI1, PCI2, and PCI3. So this is the way on developing the PCI data. So based on the eigenvalues, we get the point that the highest eigenvalues PCI data is the PC1, where the eigenvalues is 1.52, and PC2 second as eigenvalues 0.48. Alright, so we sort the eigenvectors according to the eigenvalues, and we calculate the we have the eigenvalue and eigenvector, and then if we are going to reduce the dimension, obviously, if we reduce the dimension, obviously when reconstructing the data, we lost those dimension. We choose to discard. In our example, let us assume that we consider only the x dimension, meaning that if you only reduce the dimension, obviously without the PCA, we lose the dimensions that we discard. But in PCA, we do not lose them. Yeah? So the data will be standalone. Okay. Okay. So let's continue to the Kaggle data. Okay. So in Kaggle data, first we need pandas, NumPy, matplotlib, scikit-learn decomposition using by importing the PCA from the scikit-learn decomposition, and then we import standard scalar from the scalar pre-processing, and then the scalar datasets. I use the iris data. Okay, so let's see iris. We load iris, and in iris, X is the data frame from the iris data, where the columns are the iris feature names. Okay, let's see the X hat data. So there is sepal length, sepal width, petal length, and petal width. So this data still not normalized. So we need to normalize the data using the standard scalar. So I call the scalar equal to standard scalar in the bracket. X will be scalar dot fit underscore transform the X data. So let's see the X. So we have the X here. This is the z-score of the data. So towards the mean of the z-score, what is the distance? Minus 9. Yeah? Minus 1. Okay. Minus 1. Okay. Okay, this is 0.09. Minus 0.9. Yeah? Because this is by the power of minus 1. Okay. So we have the normalized data here. And then let's call PCA using PCA equal to PCA with the bracket n underscore components is equal to 2. The principal component is PCA.fit underscore transform the X. The new X equal to data frame of data principal components, and the column name will be PC1 and PC2. So let's see the new data. So that's simple. So we have the PC1 and PC2. So we have the data there. So with this data, we can conduct clustering model using the 2-dimension rather than 4-dimension. Or if you are in using the financial ratios for the cluster, let's say you have 20 cluster, 20 ratios, you can reduce the dimension into 2-dimension to generate the clustering using 2 or 3-dimension. The clustering model cannot be interpreted as easily as using ratios, but they will be grouping into similar points, similar companies, and you need to interpret the result after the clustering. Yeah? But the clustering is referred to the whole ratios rather than you only grab 3 ratios and ignore the other 17 ratios. So using this way, yeah, the result will be more enhanced, more cutting edge. So that is the lesson for today. Forget not to like, comment, and subscribe if you like the videos. Good luck, happy studying, cheers.